All right, this is chapter 5, section 7 or 8, depending on our textbook at this time. Inverse trigonometric functions, integration. So let's dive right in. Integrals involving inverse trig functions. If u is a differentiable function of x and a is greater than 0, then we have these antiderivatives causing arcsine, arctan, and arcsecant. These are rare on the AP test, but arcsine and arctangent could come up here and there. It's important to notice that it's u over a inside of the inverse trig function, and arctan and arcsecant have a 1 over a out front, and we still have that plus c on the end. So the trick to these is determining what is u, what is a, and then using the formula. So in this first one, this looks most like the sine formula, the arcsine formula, sorry. Our a value is 2 because it's a squared, so 2 squared gives me 4. Our u value is x, which means du is just dx. Now I rewrite this as du over the square root of a squared minus u squared. And that is the exact definition of the arcsine. So we have the arcsine of u over a plus c. We just plug back in u and a. So we have arcsine of x over 2 plus c. And there's our answer. For the next one, this one doesn't have a square root in it, which tells me it's probably tangent. So in tangent, we need u and a. A squared gives me 2, which means a must be the square root of 2. U squared gives me 9x squared, so u must be 3x. Du in this case becomes 3 dx. Since that 3 is not in the problem, we need to divide by 3, multiply by 1/3 out front, du over a squared plus u squared. Now I go into my arctangent, 1/3 times 1 over a, times the arctangent of u over a plus c. Well, a is square root of 2, u is 3x, plug those in. 1 over 3 square root 2 times the arctangent of 3x over the square root of 2 plus c. Now we could rationalize these denominators, but it is not really necessary. And finally, part C here, this one looks to me the most like arcsecant. In arcsecant, our u squared gives me 4x squared, so u must be 2x, which means du is 2 dx. And our a squared gives me 9, which means a must be 3. Now the trick here is that we don't have a 2x in the front. We have just an x. So if I took this equation and solved for x, I'd get 1/2 u. Also, because du is 2 dx, we need to multiply that 1/2 out front. 1 over 1/2 of u times the square root of u squared minus a squared, and then I got my du in there. Well, 1/2 and 1/2. 1/2 divided by 1/2 is 1. Essentially, those 1/2s are going to cancel each other out. So it is a little simpler than it looked. We have 1 over a times the arcsecant of the absolute value of u over a plus c. Plug in my numbers. A is 3, u is 2x over 3 plus c, and there is our antiderivative. All right, this one you can't see, sorry. There we go. So first of all, we look for which pattern it looks like. Well, I think this one kind of looks like arcsine, but let's find out. In all of these, we would have u squared. So u in this case should be e to the x power, because e to the x squared is e to the 2x power, which means du is e to the x power dx. Well, we don't have that e to the x power in this problem, so we divide it over, just like if it was a constant. And now here's where the craziness comes. E to the x is u. So I can really say 1 over u du equals dx. Our a value here is just going to be 1. So I have 1 over u du over the square root of u squared minus a squared, antiderivative. And if we simplify that a little bit, clean it up a little, we have du over u square root u squared minus a squared. Now we see, oh, this is actually an arcsecant problem. So the answer is arcsecant, absolute value of u over a, and 1 over a out front, plus c. A is 1 though, so we just really plug back in u. Arcsecant of the absolute value of e to the x power plus c. In this case, these absolute values are not necessary because e to the x power is always positive. All right, this one doesn't look like any of our formulas. But anytime you have a fraction, you can break it up into separate fractions. So I can break this apart into x over the square root of 4 minus x squared dx plus 2 over the square root of 4 minus x squared dx. Now that first part is what we've been doing for a while now. Just basic u substitution. If u is 4 minus x squared, then du is negative 2x dx. Well, I don't have that negative 2 in there, so I go negative 1/2 antiderivative of 1 over the square root of u du. And remember, a square root can be rewritten as a 1/2 power, so this is really the antiderivative of u to the negative 1/2 power du, which is negative 1/2 times u to the positive 1/2 power divided by 1/2. 1/2s cancel, leaving me negative square root of u, which is negative square root of 4 minus x squared. All right, we've only done half of that problem. Now we go back up and do the other half. This 2 isn't really doing much in the second fraction. It's a constant out front. Now that looks like my arcsine formula. U, I'm going to call it v in this case, is going to be x, which means dv is just dx. A would be 2, so put a plus between these, sorry. We have 2 times the antiderivative of dv over the square root of a squared minus v squared. Oh, that's arcsecant, or arcsine, sorry. Arcsine of v over a plus c. Now we just plug back in v and a. So we are adding 2 times the arcsine of x over 2 plus c to our final answer. And there we have it. This problem says solve by completing the square. We're actually not going to do that. We're not going to bother with it. Same thing with this one, skipping it. We have a summary of all the different integrals we have learned about. That is in your book if you'd like. And then we still can't find certain integrals. We still don't have a way to find 1 over the square root of x squared minus 1. We have 1 minus x squared, but not x squared minus 1. We still don't have the antiderivative of natural log of x dx. So now you'll have an assignment to practice these.